Welcome back to class, everybody. Today's topic 1.3.2, how can I rewrite it? Now we're looking at zero and negative exponents. So in the last lesson, we looked at some exponents, how they behave, right? You're starting to look at certain patterns, how to divide them out and so forth. So today we're moving forward and we're going to be looking at zero and negative exponents. And we're also going to be looking at the laws of exponents. So if you guys look at the learning target for today, by the end of this lesson, I'll have formalized the laws of exponents and use them to deduce the meaning of x to the 0 and x to the negative 1. All right. So let's look at problem 173. So review what you've learned about exponents in lesson 1.3.1 to rewrite each expression below as simple as possible. If you see a pattern or know of a shortcut, be sure to share it with your teammates and provide justification for the shortcut. Okay, so we'll pretty much, since we're not working in teams today, you guys are going to be working by yourselves. We're going to be, I want you guys to try to deduce a justification by the end of doing all these examples. So let's look at part A. So what do you guys think part A would be? So you have x to the 7th times x to the 4th. Now, if we expand each x to the 7th, that would give us a total of 7 x's, right? And then if we expand x to the 4th, right, that's going to give us a total of 4 x's. So we can say that x to the 7th times x to the 4th equals x to the what? So if you guys count the total number of x's that we have, we're going to get x to the 11th power. So again, think about a relationship between these two numbers and how you can go and get that number, right? And then be mindful of what's happening right here in the middle. What's the operation between both of those? All right. So now at problem B, you have x to the 3rd raised to the 3rd power. So what do you think would be the answer for this one? So again, try expanding. That's going to be the first thing. So first you do the exponent that's outside. You're going to get x to the 3rd times x to the 3rd times x to the 3rd. And then in our next step, we're looking at, if we expand each x inside, we're going to look at 3 x's inside, right? And then another 3, and then another 3. And then our final answer would be pretty much, we have a total of, if we count them all together, we get x to the 9th power. So again, what's the relationship between the numbers, these two numbers, right, to get to that exponent? And then think about what's the operation here. Is it being multiplied? Is it being added? Is it being divided? What's going on, right? Is it being raised to the power? So think about that too when you guys are looking at patterns. In problem C, we have m to the 14th on top, and then divided by m squared, or m to the 2nd power. So if you expand everything on top, you're going to get a total of 14 m's, right? Okay, so I know I have a total of 14 on top. And then at the bottom, I'm only going to get 2. So there's only 2 ones that I have left over, right, that I can divide out. Those 2 turn into 1s. And I'm left with, right, I took away 2 from the 14. So that leaves me with 12 on top. So m to the 14th divided by m to the 2nd power is equal to m to the 12th. And again, think about what's happening right here in the exponents to get to that 12 right there. So on problem D, now we're looking at x squared times y squared and everything raised to the 4th power. So what do you think would be the answer for this problem right here? So now, if you guys think about this right here, we're looking at, you have to expand this whole thing 4 times. So I'm going to say x squared times y squared, x squared times y squared, x squared times y squared. and then x squared times y squared one more time, right? So now we're going to continue down here. In our second step, we want to expand everything that's inside. So I'm hoping that you guys already picked up some of the shortcuts, right? What's happening here? So how many twos do you have? You have 1, 2, 3, 4. So that's a total of 8 twos. So that's 8x to the 8th power. And then same thing with the y's. You have a total of 4 twos. So that's y to the 8th power. Okay. Now on the next one again, so hopefully, again, you already picked up on a couple patterns. You have x to the 5th times y to the 11th over x squared times y to the 3rd. So here, pretty much, you're going to have 5 of these on top, and then they're going to divide out with 2 at the bottom, right? So we can say that this is going to be x times x, and then times x to the 3rd. Or just let me rewrite it so we can see the big ones. So x squared times x to the 3rd, and then over x squared. And then times, we need 3 from the top one, right? Because there's only 3 at the bottom. So y to the 3rd times y to the 8th, right? These two have to add up to 11. So that's y third. And then your giant ones, so that's 1 right there. That's another one. And then you're just left with x to the 3rd power times y to the 8th. So again, think about what's happening to the exponents, right? What happens to the 5 to the 2 to get to the 3 right there? And again, it has to be dividing. And then on problem F, we're looking at 2 times x to the 12 over x to the 8th. I'm sorry, 8 times x squared. So first you want to make sure that, again, you want to simplify the 2 over 8, and then you're going to need 2 from the top one. So that's going to be x squared over x squared times x to the 10th over 1. So this is our giant 1 right there. And then remember, this is 2 times 1, and then this is 2 times 4. And then you have like a giant 1 right there. So there just has 1 over 4 times x to the 10th. And you can always rewrite this as x to the 10th over 4. So now, using the table below, summarize the patterns you found in problem 173 for each expression in the table. For each expression in the table below, rewrite the given expression in simpler form and then write an expression that represents its generalization. Then in your own words, explain why the pattern works. So if we have x to the 25 times x to the 40th, so we can rewrite this as x to the 25 plus 40 on the exponents, and that would give us x to the 65. So if we want to generalize that, we would say x to the m plus n, right? And why do you think this is true? So I'm going to leave that part to you. Right? So one of the explanations could be that you pretty much, when you expand, right, you're adding, you're putting things together. So by expanding, right, you're naturally putting things more and more together, right? So by expanding, you can see the pattern grow. How many you have? All right. So if we're dividing, so we have x to the 36 over x to the 13. So now here, what you do with the exponents, again, if you picked it up, if when you're dividing, you subtract the exponent, so x to the 36 minus 13, and that equals x to the 23. So again, if you want to generalize that statement, you would say x to the m minus n. All right, in this explanation, again, I'll leave it to you guys. Give me what you think right here. This is going to be an open-ended question. So one of your explanations, again, could have been that when you're creating, right, when you find the giant ones, right, when you find the giant ones, then pretty much that's when you can take away and simplify, right? You can take away and simplify. And the thing you're simplifying would be pretty much the exponents. Oops. Oops. All right. And then let's look at the last one right there, part C. So x to the fifth raised, right, raised to the 12. So if you notice here, we're going to have 12 groups of 5. So when you guys are counting groups, when you put them in together, you're just basically multiplying. So this would be x to the 5 times 12, and that gives us x to the 60. And again, look at the previous problem, and you can see what's going down. So x to the m times n, right? So here you can say you create groups. You can create groups, right? You create groups, and then by counting the groups, you can find its multiplication.